Okay, so now that you've got a sense, hopefully, of like what Gauss's law is and how it's useful, we're just gonna go through like how to actually use it. So to do that, as I mentioned in the first video, you need to sort of like manipulate the symmetry of the problem. And there's really only three different symmetries that are possible. So I'll go over examples of each one. But the overall goal here with Gauss's law is to use the geometry of a charge distribution to find the E field without having to use a complex integration. So like you're basically manipulating, so you're using the geometry and ideally the symmetry of the charge distribution to find the E field without having to use complex integration. So Gauss's law is really just it's almost like a trick. Okay, it's a tool for finding the E field. So recall in the first video, we said that the flux has actually two definitions. It's equal to the Q enclosed by some imaginary Gaussian surface that I get to choose myself, divided by epsilon naught. And it's also equal to the electric field times the area, right? It's really equal to the surface area. Um, but that simplifies down to this, assuming the E field is parallel to the area vector. So those two things have to be parallel, and then you can just multiply them together. Okay, otherwise you have to do the surface integral. Okay, but that's where the symmetry comes in. Okay, so there's 5 steps that you can follow in every single Gauss's law problem. And I'm just going to go through those 5 steps. And if you kind of like remember what the 5 steps are, or you refer to them whenever you have to solve a problem like this, you'll never go wrong. They're very formulaic, these problems. Okay, so the first step is to identify which symmetry you can use. Okay, so identify the symmetry of the problem. And I'll show you how to do that. It's quite easy. Okay, there's really only 3 choices. Okay, there's only 3. Um, it can either be spherically symmetrical, so it could be spherical, it could be cylindrical, or it could be planar. Okay, and that's it, really. Those are the only 3 to choose from. Okay, so once you like pick one of the 3, the second step is for you to choose based on that symmetry or your Gaussian surface. And like so you're picking the shape based on the symmetry, and then you're picking like where it's drawn based on basically where you want to find the field. You always draw your Gaussian surface so that it's like crossing the spot where you're trying to find the field. Okay, so that's step 2 is choose your Gaussian surface. And a Gaussian surface, this confuses a lot of people when they're first learning this. It's not a real surface. It's like a hypothetical. It's sort of like a mental like construct that you use to manipulate the symmetry. So it's a hypothetical closed surface where the E field magnitude is constant and parallel to the area vector of the surface. Okay, so you're basically choosing the surface such that the E field, like at that surface, is constant and also pointing in the same direction as the area vector. Okay, so that you can say this is true. Okay, step 3 is to calculate the flux. Calculate the flux. Okay, through that Gaussian surface, right? So you know that it's just like E dot dA, but that equals E times A. Okay, assuming we've chosen our surface correctly. And then step 4 is to calculate the enclosed charge. Okay, Q enclosed. Okay, basically like using sort of like a similar exercise to what we did at the end of the first video. Okay, and then the last step, because I mean the reason I do that is because I know that flux also equals Q enclosed over epsilon naught. And then the last step is to like set those two things equal to each other and to solve for the electric field. Okay, so step 5 is to set like I don't know, we could call this like equation 3 and call this equation 4 for flux, right? So set equation 3 equal to equation 4 and then solve for the E field. Okay, so like you set EA equals Q enclosed over epsilon naught, and then you just isolate. So this is Q enclosed over epsilon naught divided by the area. Okay, so all of the problems follow these 5 steps. Okay, so now the rest of this video, I'm just going to go through each of these different symmetries and show you 1 or 2 examples, and then you really will you'll know that's all there is to know about Gauss's law. Once you know the 3 symmetries and you know how to apply them, you're all set. Okay. So the first one that we're going to talk about is the spherical symmetry. And so you know how to use I think you'll see quickly that it's like very obvious. Like when you see a charge distribution, it becomes like pretty obvious like which symmetry to use in which situation. But just to be explicit about it, you use a spherical symmetry when the charge density depends only on the distance from like some center point. Okay, so you use it when the charge density, like your distribution of charges, depends only on the distance, the distance from some center point. So basically, like it has sort of like an R dependence. Okay. Um, there's really 3 categories of spherical situations. Okay, there's a single point charge, there is a spherical shell, and then there's a uniformly charged sphere. So we're going to talk about each of those in turn because they come up like frequently. Okay, so let's do the first one, the single point charge. We've kind of already done it. It's like it's very easy. So you've got a charge. Okay, let's just say it's a positive charge, but it doesn't have to be. And you know that the field lines go out like this. Okay, that's the electric field lines. Okay, and let's just say I want to find I want to know what the E field is right here at point P. Okay, I want to know like what is the E field right there. Okay, at this point here. Okay, so I hope it's easy to see that if I drew a spherical Gaussian surface, like one that looked like this, at the point that I'm interested in, in that case, the E field lines, which maybe I should label for clarity. So these are the E field lines, the blue lines. Those are in the same direction. They're parallel to the area vector. Remember in the tutorial, we made a big deal of like drawing the area vector. So these are like the area vectors, right? So the area vectors, remember, are perpendicular to the surface, okay, at every point. So if I draw a Gaussian surface around my point charge, the area vector is parallel to the E field. Okay, so that's good because that means that when I write out my formula for flux, right? So remember, flux is the surface integral of the electric field at point P, which is where I'm interested in, right? But because I've met the condition of the E field being parallel to the area vector, it's just the electric field times the area, the surface area of that Gaussian surface. Okay, so that's one definition of flux. My other definition of flux is it's the Q enclosed divided by epsilon naught. Okay, so I set these two expressions equal to each other. So it's E times A equals Q enclosed divided by epsilon naught. Okay, and the A is just the surface area of my Gaussian surface. Okay, and I've drawn that a distance. I should define that distance. I've drawn that a distance r from the center of my, or from where my charge is, right? So I'm just going to call that capital R. Okay. So the area of that's the surface area of my Gaussian surface is just 4 pi r squared. Okay, so the electric field is going to be Q enclosed, which is just my positive Q, divided by epsilon naught, and also divided by the area, which is just 4 pi r squared. And that's the answer, 4 pi r squared. So that would be what this expression here would be, what the electric field would be at that point, P. Okay, so that's the single point charge. Let's go over the example. Hopefully that was clear. That's sort of the simplest case. That's one. Okay, so let's do two, the spherical shell. So a spherical shell is just exactly what it sounds like. It's just a shell. And the charge is all on the outside of that shell. Okay, for reasons that you will understand in the next section. Okay, the last section of this chapter explains why when you have like a cavity, the charges all sort of migrate out to the edge of that cavity. Okay, so in any case, just accept the fact that we've got this configuration, this geometry of charges. So let me draw the E field in blue again. So it's going to look the same, right, as my point charge. It's going to radiate out in space. Okay. And let's say, again, I want to find the electric field at this point P here. E equals question mark. Okay, the procedure is exactly the same, and hopefully you can see like that this also has a spherical symmetry, right? Like it's the radial distance from the center that matters. So I would let me draw my Gaussian surface in green again, just to be consistent. So I would draw my Gaussian surface spherically because it manipulates the symmetry of the problem. And I would draw it like at P because that's where I care about the field. Okay, and actually, I mean the solution um, is is the same, really. Let's call let's call this the radius of the shell, and let's call what color can I use? This the radius of my capital R, the radius of my Gaussian surface. Okay. So it's the same sort of like procedure. I write out the formula for flux. So the condition of the electric field and the area vector being parallel has been met. So I can just say that the flux is equal to the electric field times the area of my Gaussian surface. I can say that the flux also equals Q enclosed divided by epsilon naught. Okay, and the problem would this type of a problem would define like the Q on the spherical shell as like let's call it like uh capital Q, right? It's distributed all over like all over. It's kind of like all of that charge is like smeared on the outside of the spherical shell. Let's just call that like collectively capital Q. Okay, so that would be Q over epsilon naught, and that's going to equal E times the area. And it's the same deal. It's 4 pi capital R squared because the capital, not the lowercase r, but the capital R, because it refers to my Gaussian surface. And so the E field is just going to be Q over epsilon naught 4 pi R squared. Okay, and that, I mean, it's the exact same sort of result as what we saw with the point charge. Okay, so like Q enclosed, or sorry, Q enclosed in this case just equals capital Q. Okay. What if the problem asked you to calculate the E field inside the sphere. So let's say that it said like what is the E field where R, like capital R, is smaller than like the radius of the sphere. Okay, that's sort of how that is expressed. So like basically like inside the shell. So to solve that, I would just draw another Gaussian surface inside the sphere. Okay, so I would draw like remember we're making Gaussian surfaces green. So I would draw my Gaussian surface here such that the radius of that one, the radius I should call this like a different like I'll call that R2. Um and maybe this one R1. R1, R1. Um, so the radius of the Gaussian surface is smaller than the radius of the shell. Okay. So that is actually a very interesting result. So you would follow the same procedure. You would say like the flux equals E times A. It also equals Q enclosed divided by epsilon naught. Okay, so you could say that E equals Q enclosed divided by area times epsilon naught. But inside the new Gaussian surface, the R2 Gaussian surface, the Q enclosed is equal to 0. So the E field inside that shell is equal to 0. Okay. The third part of this module or this lesson on collage, or sorry, not the third part, the fourth part explains like why this is true, why the E field inside a conductor is 0. But this like proves it like mathematically with Gauss's law. Okay, so that's situation 2, the spherical shell. The last situation to look at is the uniformly charged sphere. Okay, and there's an example. The uniformly charged sphere is a little bit more complicated. because it's like it's not just a shell, it's a sphere, it's a sphere. So it's got like here's an example of a problem that you might encounter that falls into this category. So it's like a solid sphere of radius r and has a total charge q, and it's uniformly distributed throughout the sphere. Okay, with a charge density of like rho naught. So in this situation, like so rho naught is referring to the amount, so like the amount of charge, so like that total charge divided by the volume. Okay. So like how is situation like 3 different from situation 2? Well, situation 2 is sort of like a 2-dimensional thing, and situation 3 is a 3-dimensional thing. We're talking now about a volume. Okay, it's like a sphere, whereas 2 is just a shell. Okay. So okay, so let's go through that. So we're and this problem asks us to get again figure out what the electric field would be inside the sphere and outside the sphere. Okay, so let's do outside the sphere first. So let's draw it. Okay, so I'm gonna draw so that's my sphere. And you can call, I mean, it's up to you like how you define it. Let's call the radius of the sphere capital R. Okay, and then oh yeah, just because like in this problem, it defined it. Okay, so like I know in the last problem I switched like capital R, lowercase r to mean different things, but like you can define it however you want. But so in the problem it says radius r is the radius of the sphere. Okay, and we want to find the E field first outside the sphere. So we're going to draw our Gaussian surface outside the sphere. Okay. And we're going to define that as like lowercase r. Okay. So in the first case, lowercase r is bigger than uppercase r. Okay. So you follow the exact same procedure. So the flux is equal to E times A. For the same exact reasons, like the field lines, or I did those in blue before. I guess I should be consistent. Like the field lines are radiating radially, right? And so the electric field lines are going through the Gaussian surface parallel to the area vector, okay, which is the condition that we need for this to be true. Okay. And then I know that flux also equals Q enclosed divided by epsilon naught. Okay. So if I want to find the electric field, I just set those two things equal and solve for electric field. Okay. The area is always the area, the surface area of my Gaussian surface. Okay. And because my Gaussian surface is outside the solid sphere, the Q enclosed is the total Q. Okay, so I can just write for Q enclosed, I can just write Q because it's like it's got all of it inside there. Okay, divided by epsilon naught. And then the area is just 4 pi times little r squared because that's the radius of my Gaussian surface. Okay, so that's the answer to part A. Okay, like the electric field is just that expression. Okay, part B is a little bit more complicated because I'm going to redraw it so the diagram doesn't get like confusing. So yeah, I'll just use the same color. Okay, so part B, I've got my sphere, it's a radius r. You know, my field lines are out like this. And I mean, I should have like there's charge all throughout here, all throughout the volume. So my field lines really should have extended like I shouldn't have just drawn them from the surface. That was dumb. Like I should have, yeah, they extend inside the surface as well. Okay, so like just to make that clear. Okay, so that those are my E field lines. But now with part B, I have to draw my Gaussian surface inside the sphere. Okay, so I'm gonna draw it like it doesn't really matter where, just inside. Okay, and I'm gonna call that radius little r for my Gaussian surface. Okay, so it's again the exact same procedure. Flux equals E times A, which equals E times 4 pi lowercase r squared. Okay, that's flux. Flux also equals Q enclosed over epsilon naught. But now the Q enclosed is not equal to the total Q that was defined in the problem. We have to use like the geometry to find out how much Q is inside my Gaussian surface. Okay, so there's sort of like an extra step with this one, which I'll do over here. So I know that the charge density is just equal to the charge divided by the volume. Okay. And like in the total sphere, like the total charge is just uppercase Q, right? And the volume of a sphere, I don't know if you remember this from like middle school, is 4/3 pi. And I'm gonna use a capital R um uh to signify the fact that I'm using like the whole sphere. Okay, so like the total charge divided by the volume of the total sphere. Okay, so my Q enclosed is going to be a smaller value of that, right? It's going to be equal to rho naught, like the density, times 4/3 pi lowercase r cubed. Okay, to signify like that it's only like the part of the sphere that's inside my Gaussian surface that is accounted for in that Q enclosed. Okay, so like that's the expression for Q enclosed. So I'm just gonna rewrite it over here. It's just rho naught times 4/3 pi r cubed divided by epsilon naught, right? That's the flux. And that equals E times 4 pi r squared. Okay, so I can isolate, I can like rearrange this and cancel things out. And it reduces down to just rho naught times lowercase r divided by 3 epsilon naught, which is pretty cool. It's a very neat expression. And that's in the condition if you're inside, like if your Gaussian surface is smaller than the radius of the sphere. Okay. That's spherical symmetry. That's like really all, I mean, if you understand those three cases, you understand everything to do with spherical. It doesn't get any more complicated than that. I mean, sometimes there are sort of like spheres inside spheres that have different charge distributions, but I mean, it follows the exact same pattern. Okay, so now we're going to talk about cylindrical symmetry. The other two are, I think, more straightforward. So cylindrical symmetry, like when you use it, is whenever the charge density depends only on the distance from like some sort of axes. Okay, so like here, let me write that just so you have it. So when the charge density depends only on the distance. So instead of like the distance from the center of a circle, It's the distance from an axis. Okay. So like for example, i.e., like the one that you constantly run into is an infinitely long wire is like the typical one. Infinitely long wire. Or like an infinitely long cylinder. Okay. Those are the two like main ones. Okay, so let's look at like and let's look at the example. Um, well, I'm gonna do like just a basic example so you see the pattern, and then I've got like a more I've just got two examples basically. Okay, so let me do one here. So let's say that you have like an infinitely long wire. Okay, and it's got like an even charge distribution. Okay, like all the way along it. Um, so here, and I want to know, and it's same question, always same question. So I want to know what the electric field is at some specific distance away from the wire. Okay, I'm not going to draw it all the way. So yeah, let's say like I want to know what's the E field here at point P. Okay. So because it's like the symmetry is cylindrical, like all the only thing that matters is like how far you are from like some axes. What I can do is instead of drawing a Gaussian surface that is spherical, I can draw a cylindrical one. Okay, so I'm going to draw my Gaussian surface to be a cylinder such that it goes through P. So maybe let me start with this part of the cylinder so that it goes through P. And then that's like the cap. Okay. So that's my Gaussian, and I didn't draw out a dotted line. I should have drawn a dotted line, but you guys get it, I think. Okay, this is a dotted line. Da, 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 da. Okay, that's my Gaussian surface all the way along. Okay, so this is my Gaussian surface. Okay. And I'm going to define some like some geometry things so that I can refer to them. So I'm going to say that P is a distance R from the axes. Okay. And I'm gonna say the length of my cylinder is L. Okay, I'm just gonna call that L. Okay. So there's two sort of like if you think of the cylinder, there's two parts to it. There's the curved side, and then there's the end parts. Okay, so the end parts, um, the flux is zero, right? I think you can see that. Like, remember from the tutorial, like the area vector of those end caps would be pointing out like this. That would be the area vector. And the E field is exactly perpendicular, like to the area vector, right? At that point. Um, so the flux, so like if we break the cylinder down into like the curved part and then the end parts, the end, I don't know what you want to call them, the end caps. Um, in the end cap part, the E field is perpendicular to the area vector. Therefore, the flux is zero at the end caps. Okay. For the curved parts, um, we've got the perfect situation that we love, right? The electric field is parallel to the area vector, which allows us to say that the flux is just equal to the electric field times the area. Okay. So that's really good. Okay. So um the flux is going to be equal to E times A, and the electric and the area is just going to be 2 pi times R times L. Okay. And we would probably be told in the problem what lambda is of the wire. Remember from last week, lambda is the amount of charge per unit length. So like the problem would have to define lambda. And then you would say, well, the Q enclosed is just equal to lambda times L, right? It's like that's how much charge is enclosed in my cylinder. And so the E field would just be equal to Q enclosed divided by epsilon naught, which would just be lambda over L divided by epsilon naught. And then I would set that equal, um, sorry, that's flux. I would set that equal to the other expression for flux. So I would have something like E times 2 pi RL equals lambda L over epsilon naught. The L's would cancel, right? And so I'd have E equals lambda divided by 2 pi R epsilon naught. Okay, so this this example. Oh, this example is different. I'm sorry. Yeah, I was like, oh no, I've done the same example twice. Okay, so let's look at this example. Um, so we've got an infinitely long shell um, of radius r, and it has a uniform surface charge of sigma. Find the electric field outside the shell. Okay, I think to make this like clearer, it would have to say cylindrical shell, right? Because otherwise, I don't know how you would differentiate it. Like the problem would have to say, well, no, maybe it wouldn't because infinitely long. But anyway, it's a cylinder. Infinitely long, I guess, implies cylindrical. It's a cylinder. Yeah, I guess the fact that it said infinitely long means like we have to know it's a cylinder. So here's the cylinder. Okay, I'm just going to draw like a segment of it. Okay, and the charge is like all over it, right? It's a surface charge, so it's like all over the surface. Okay. So the field is like going out. I mean, I'm just going to draw it in 2 dimensions because I can't do it in three. But the field is going out in kind of all directions from that cylinder, right? And like out towards me. So I would draw um like a cylindrical Gaussian surface around the outside of that, right? And this cylinder, we've been told it has a radius of r, capital R, so that's capital R. And we want to know like what is the E field like out here, right? Like at some distance further than the radius of the actual cylinder. So I would draw my like Gaussian surface like out here so that it encompasses, sorry, I drew that badly, but you get the idea. It encompasses the whole thing. And I mean, these field lines, of course, like they go all the way through, right? They don't end there. They go all the way through space. Okay, so it's the exact same, it's the exact same deal. I've been given a sigma now, which is a charge per area. Okay. And I can figure out what the Q enclosed is just by multiplying sigma times the area of the cylinder. So the cylinder has a radius of capital R. So it's going to just be sigma times 2 pi capital R times L. Okay, so that is going to be the Q enclosed. Okay, so now I'm gonna write out my two expressions for flux. So flux is going to equal the electric field times the surface area of my Gaussian surface. So that's just going to be E times 2 pi lowercase r times L. Because remember, lowercase r is the radius of the Gaussian surface, whereas uppercase R is the radius of the actual cylinder. So that's why we use capital R here when we're trying to figure out like how much charge there is on the cylinder. And we use lowercase r here because that corresponds to our Gaussian surface. Okay, so that's one expression for flux, and then the other expression for flux is just Q enclosed over epsilon naught. We've already worked out that Q enclosed is equal to sigma times 2 pi capital R times L. So that's going to be all over epsilon naught. So then we set these two expressions equal to each other and solve for E. So this is going to be equal to sigma over 2 pi capital R divided by L divided by epsilon naught and then 2 pi lowercase r times L. And then there are some things that cancel. So the 2 pi cancels with the 2 pi, the L cancels with the L, and you're left with sigma capital R on the top divided by epsilon naught lowercase r on the bottom. Okay, and so that would be the electric field. Some, some distance, like lowercase r away from a infinitely long cylindrical shell. All right. Cylindrical geometry. Okay, the last one to do is the planar the planar symmetry. So when do you use this one? So you use this when the charges are uniformly spread over a large flat surface, like an infinite plane. Okay, and the field points away from the plane. Okay, so you use it when the charges are uniformly spread over a large flat surface. Okay, like the classic is the infinite plane situation. Okay, and I've included a diagram from the textbook just because it's really hard to draw. I didn't have any confidence in my ability to draw this. But so like let's just kind of look at what this is. So when you have a planar symmetry, you draw what's called like a pillbox. Okay, it's a strange it's like the surface, the Gaussian surface that you draw is referred to as a pillbox. It's basically just like a rectangle or a cube that sort of like spans like above and below the planar surface. Okay. So like there's a top and a bottom to it, right? That is kind of shaded here in orange in the diagram. Like the box that you see is the Gaussian surface that we've chosen to manipulate the symmetry of the plane. So it's got a top and it's got a bottom underneath here. And those two surfaces meet our requirement of the area vector of that surface being parallel to the electric field, right? The electric field, like the charges are like all over the plate. So the electric field lines are going like up and down. They're drawn in red here, right? So they're going up and they're also going down. Okay, like if we were to look at it from the edge, like it might be easier to look at it from the edge. Like you've got charges all along this plane. The electric field lines would look like this. Okay, and then I would draw my Gaussian surface kind of like this. That would be my pillbox. Okay, so you can see that it's only going to be like the top surface and the bottom surface that actually contribute to the surface area integral, right? Like the sides don't on the sides the electric field is perpendicular to the area vector, and so none of the four sides contribute to the flux. The flux is zero. Okay, so if we were to write out like an expression for electric flux, like going back to this idea of like the surface integral, so it's going to be like the electric field at some point P that I'm interested in, times the area. Okay, so like it's going to be like the electric field times A of the top, right? Like let me write this top plus the electric field times the area of the bottom. Okay, plus 0 plus 0 plus 0 plus 0, where these are like the four sides of pillbox. Okay. So the flux therefore is just equal to 2 times the electric field times the area, right? Because it's just the top and the bottom that contribute. Okay. So that's one way of expressing flux, and then the other way is to say that it's the Q enclosed divided by epsilon naught. Okay, and it's the same deal. It wasn't defined, but the way that these problems are expressed charge, it's sigma, which is charge per area. So they would say like there's some sigma on this infinitely large plate, which represents a charge per unit area. Okay, so the Q enclosed, therefore, is just going to be sigma times A. Okay, so I would write that down here, sigma, where A is like the area of like either the top or the bottom, right? So sigma times A divided by epsilon naught. Okay. And so then I just like set these two equations as I did in all the other examples. I set these two equations equal to each other. So 2 times electric field times area equals sigma area epsilon naught. And so electric field, so the areas cancel. So electric field is going to equal sigma divided by 2 epsilon naught. Okay. And this is like at some point, like where is this? This is like at some point, like up here, like away from the plane. Okay, because this is an infinitely, and we talked a little bit about this, or we talked a little bit about this in the tutorial last week, but because it's an infinite plane, it doesn't matter where how far up you are, like how far away from the plane you are in terms of the strength of the E field. Okay, and you can kind of see that here. There's no like Z dependency. Okay, so this would be the E field at like at any point Z above the plane. Okay, and I think that's it. I think that's it. So yeah, Slack me if you have any questions. And I'm hoping that like all of those examples will help you the challenge problems were like very carefully selected. I mean, more so this week than any other week because of the just like the complication of the like, the math is a little bit complex, but I'm hoping that these examples will help you with the challenge and just let me know if you have any questions. Cylindrical geometry. Okay, the last one to do is the planar geom, the planar symmetry. So when do you use this one? So you use this when the charges are uniformly spread over a large flat surface, like an infinite plane. Okay, and the field points away from the plane. Okay, so you use it when the charges are uniformly spread over a large flat surface. Okay, like the classic is the infinite plane situation. Okay, and I've included a diagram from the textbook just because it's really hard to draw. I didn't have any confidence in my ability to draw this. But so like let's just kind of look at what this is. So when you have a planar symmetry, you draw what's called like a pillbox. Okay, it's a strange it's like the surface, the Gaussian surface that you draw is referred to as a pillbox. It's basically just a rectangle or a cube that sort of like spans like above and below the planar surface. Okay. So like there's a top and a bottom to it, right? That is kind of shaded here in orange in the diagram. Like the box that you see is the Gaussian surface that we've chosen to manipulate the symmetry of the plane. So it's got a top and it's got a bottom underneath here. And those two surfaces meet our requirement of the area vector of that surface being parallel to the electric field, right? The electric field, like the charges are like all over the plate. So the electric field lines are going like up and down. They're drawn in red here, right? So they're going up and they're also going down. Okay, like if we were to look at it from the edge, like it might be easier to look at it from the edge. Like you've got charges all along this plane. The electric field lines would look like this. Okay, and then I would draw my Gaussian surface kind of like this. That would be my pillbox. Okay, so you can see that it's only going to be like the top surface and the bottom surface that actually contribute to the surface area integral, right? Like the sides don't on the sides the electric field is perpendicular to the area vector, and so none of the four sides contribute to the flux. The flux is zero. Okay, so if we were to write out like an expression for electric flux, like going back to this idea of like the surface integral, so it's going to be like the electric field at some point P that I'm interested in, times the area. Okay, so like it's going to be like the electric field times A of the top, right? Like let me write this top plus the electric field times the area of the bottom. Okay, plus 0 plus 0 plus 0 plus 0, where these are like the four sides of pillbox. Okay. So the flux therefore is just equal to 2 times the electric field times the area, right? Because it's just the top and the bottom that contribute. Okay. So that's one way of expressing flux, and then the other way is to say that it's the Q enclosed divided by epsilon naught. Okay, and it's the same deal. It wasn't defined, but the way that these problems are expressed charge, it's sigma, which is charge per area. So they would say like there's some sigma on this infinitely large plate, which represents a charge per unit area. Okay, so the Q enclosed, therefore, is just going to be sigma times A. Okay, so I would write that down here, sigma, where A is like the area of like either the top or the bottom, right? So sigma times A divided by epsilon naught. Okay. And so then I just like set these two equations as I did in all the other examples. I set these two equations equal to each other. So 2 times electric field times area equals sigma area epsilon naught. And so electric field, so the areas cancel. So electric field is going to equal sigma divided by 2 epsilon naught. Okay. And this is like at some point, like where is this? This is like at some point, like up here, like away from the plane. Okay, because this is an infinitely, and we talked a little bit about this, or we talked a little bit about this in the tutorial last week, but because it's an infinite plane, it doesn't matter where how far up you are, like how far away from the plane you are in terms of the strength of the E field. Okay, and you can kind of see that here. There's no like Z dependency. Okay, so this would be the E field at like at any point Z above the plane. Okay, and I think that's it. I think that's it. So yeah, Slack me if you have any questions. And I'm hoping that like all of those examples will help you. The challenge problems were like very carefully selected. I mean, more so this week than any other week because of the just like the complication of the like, the math is a little bit complex, but I'm hoping that these examples will help you with the challenge, and just let me know if you have any questions.